Hello dear students, welcome to the course of Engineering Thermodynamics. Myself Mistry, Assistant Professor from Mechanical Department of LJIET Institute of Engineering and Technology. So today we are going to discuss about the chapter combustion. So let us start with the combustion. So what is combustion? Let us understand that. So if you will burn any substance in the presence of complete oxygen, enough oxygen, then it will be known as combustion. Okay. So here, first, before understanding the combustion, let us understand the constituent that are used for the supply of complete combustion. Okay, so as you can see on the given screen, the table is there, that is air constituent. So here air is constituent of two gases, that is oxygen and nitrogen. Oxygen is present 23% by mass and 77% is present as nitrogen by mass. Okay, and if you take by volume, then oxygen present in the air is 21% and nitrogen present is 79%. So keep these values in your mind because it will be helpful in solving the examples. Okay, so simple, the meaning is very simple. If you take 1 kg of air, then in that 1 kg of air, 23% portion or 230 grams will be occupied by oxygen, that mass, and remaining 770 kg or 770 gram of nitrogen will be there, okay, in the air of 1 kg. Same way, if you take air of 1 meter cube volume, then 210 or 0.21 meter cube of volume will be occupied by oxygen and 0.79 meter cube of volume will be occupied by nitrogen in that 1 meter cube of air. Clear? The meaning is simple. Now here N2, that is nitrogen, is inert gas. Inert gas means it will not take participation in any reaction. So from the reaction side and from the product side, it will remain as it is. Okay, so keep this thing in your mind. Now further, let us understand the combustion of methane. So for example, methane is CH4. So CH4 plus O2 will give me CO2 plus H2O. Here the equation is chemically balanced, that's why twice O2 and twice H2O is written. Okay, so for the theoretical air or stoichiometric air, see here the equation is chemically balanced. That means whatever amount of oxygen is required for complete combustion of methane is written over here. That is why that much air is known as theoretical air or stoichiometric air. That is nothing but the minimum amount of air required for complete combustion. That is known as stoichiometric air or theoretical air. And you remember students, complete combustion means what? There is no oxygen in the products. Okay, so that is the meaning of complete combustion. Okay, also you may note that if you are having CO, carbon monoxide, as your product, then it will be known as incomplete combustion. And if you have CO2, that is carbon dioxide, then it will be known as complete combustion. Okay, the left side of the equal to sign in chemical equations will be known as reactant and the right hand side of the equal to sign will be known as products. Okay, now let us understand certain definition. Excess air. So excess air is very simple. Amount of actual air minus theoretical air. See what will happen, students. On paper you should supply the theoretical air or stoichiometric air for complete combustion, but in actual practice you have to supply more than the theoretical air. That is known as excess air. Difference between these two, actual air that you have supplied and amount of theoretical air that is required, that difference will be known as excess air. Simple. So the convention for writing the excess air is this, that is 50% theoretical air is supplied or 50% excess air is supplied. Okay, air fuel ratio, simple, mass of air divided by mass of fuel. And fuel air ratio, simple, mass of fuel divided by mass of air, right? Same way stoichiometric air fuel ratio, that is mass of stoichiometric air divided by mass of fuel, and percentage of excess air. So that is nothing but air fuel ratio minus stoichiometric air fuel ratio divided by stoichiometric air fuel ratio. That will give you percentage of excess air. And the last one is equivalence ratio. That is very simple, stoichiometric air fuel ratio divided by actual air fuel ratio. These are just ratios and you have to keep this in mind. Okay, now adiabatic flame temperature, very simple students, that if you will do combustion in open environment, then you cannot achieve maximum flame temperature. But if you will do the combustion in closed or well maintained adiabatic environment, then you can achieve the maximum temperature. So in complete adiabatic environment, the temperature that the flame or the combustion has achieved will be known as adiabatic flame temperature. But in real life, in real practice, you cannot achieve complete adiabatic environment. So in real life, adiabatic flame temperature that you are achieving or you are gaining is less than the ideal adiabatic flame temperature. Okay, so that is why this thing is explained like this. Okay, also the need, that is high temperature required in rocket propulsion, high temperatures are required. But what will happen? Due to metallurgical condition, you cannot increase the high temperature, right? So maximum temperature is only possible when it is completely adiabatic process. Okay, but it is not completely adiabatic because it is difficult to achieve the adiabatic conditions. Okay, so it is ideal concept that in under adiabatic condition, ideal under adiabatic condition, if you attain maximum value of temperature, that is known as adiabatic flame temperature. Okay, and it can be controlled by amount of excess air supply. And in actual practice, the actual temperature is less than the adiabatic flame temperature. Why? Because the reasons are given: heat loss, then incomplete combustion, then dissociation of products into other chemical compounds, right? So these are the reasons. Now, calorific values, there are two kinds of calorific values: higher calorific value and lower calorific value. Let us understand. Simple. The meaning of calorific value is very simple: amount of heat released by burning a particular unit of a substance. Okay, that is known as calorific value. Okay, so generally higher calorific value and lower calorific value, two terms are there. So higher calorific value is very simple. When you have water in the product side, that is your H2O is in the liquid form, then it is known as the higher calorific value. And if you have H2 in gaseous form, then it is known as lower calorific value. Now question might arise in your mind, sir, why is it so? Because simple students, see, in case of H2O is in gaseous form. Now, if you want to convert the H2O gas into H2O liquid, then just think logically. What you have to do? You will have to reject the heat, because during the condensation, what will happen? During condensation, H2O gas to H2O liquid, during condensation, you have to reject the heat. So if you will reject the heat, then it will be added, right? So here in higher calorific value, what will happen? You are condensing it. H2O is condensed, so that much extra heat is provided, or that much extra heat is gained by us, right? So that is why higher calorific value will be there. And in lower calorific value, the calorific value will be less. Clear? I hope it is clear to you. Now, calorific values are of two types. For measurement, we can consider two segments, that is solid and liquid fuel and gaseous fuel. So for solid and liquid fuels, you can use bomb calorimeter, and for gaseous fuel, you can use Junker gas calorimeter. So let us understand the bomb calorimeter first. Very simple. Let us understand the diagram given on the screen for the bomb calorimeter. Okay, so here let us start from the left hand side. This is the insulation jacket. Then in the insulation jacket there is airspace provided, and in that airspace a bucket is placed like this, right? I hope you can see, that is dark green color, that is bucket. Okay, now in this bucket water is filled, and in this water some bomb is placed. Okay, here also heater is provided. This heater option is optional, so it might be present or it might not be present according to the manufacturer. Okay, then ignition coil is there. Ignition coil is there. Then steel bomb is there. This is the steel bomb, right? This whole structure is steel bomb. Okay, and then sample is there. Sample is the fuel of which you want to measure the calorific value. Then crucible is there. So crucible is also present. Okay. Now, one more thing, thermometer is there, right? Then oxygen supply will be there. Then ignition wires will be there. These are the two ignition wires that are connected with this coil, ignition coil, and the stirrer is present. Okay, so now these are the arrangement or these are the devices that will be used in bomb calorimeter. Okay, I told you heater will be optional according to the manufacturer. Okay, so let us understand the construction. So construction is simple. Bomb is generally made of SS and it is able to resist the pressure up to 100 bar, and crucible is generally made of silicon or quartz material. Okay, so remember the materials. Bomb is SS and crucible is generally quartz or silicon. Next, let us understand the working of the bomb calorimeter. The very first thing is very simple. See, I will give you a brief idea what will happen. See, let us consider that you will take the sample over here. Okay, this sample is in contact with this ignition coil. Okay, and here in this bomb you will supply enough amount of oxygen, that is stoichiometric air. Okay, more than that you will supply over here. Okay, and this bomb is completely closed. Okay, and it is dipped into this water and stirrer will be continuously rotating. Okay, so now what will happen, through this ignition wire you will supply the current for, let us say, 2-3 seconds. So what will happen, if you will supply the current, then according to I square RT, heat will be generated, and due to that this sample which is in contact with the ignition coil will start burning or combustion will start, because you have already provided enough amount of oxygen. Okay, so as soon as the combustion will start, then the temperature and pressure inside this bomb cavity will increase, and this increase in temperature will be transferred to the water outside. Okay, and now here the role of stirrer will be very much important. What is the function of stirrer? Stirrer is used to distribute the temperature of the water uniformly. Okay, there is a term called as thermal stratification. Thermal stratification means what, students? If water is not disturbed or kept constant, okay, steady water, then after a certain time what will happen? The layer of temperature will be there. Okay, the layer of temperatures will be there throughout the water. Same temperature will not be maintained for every layer of the water. So in order to avoid so, constant disturbance is provided by the stirrer. Okay, so uniform temperature distribution will be there. Okay, so now this rise in temperature will be noted by this thermometer, and you will observe and note down the maximum temperature rise. You know the minimum temperature also, starting temperature of the water also, and you have noted down the maximum temperature also. You might be knowing the sample weight also. Okay, mass of the sample also. Okay, so now this is the brief procedure. Now let us understand that again. So working is very simple. Crucible and calorimeter. So as I have told you, crucible and calorimeter is prepared. Okay, then specimen is placed in the crucible. Okay, then oxygen is added, then bomb is submerged into the water. Then what will happen? Water and bomb are enclosed in the calorimeter. This is known as calorimeter. Okay, this whole thing is known as calorimeter. Okay, next, stirrer is on, switched on, and at equilibrium current will be passed. See, initially what will happen, stirrer will be started and you will wait for 5 minutes. So the temperature will be distributed uniformly, and then you will pass the current. Okay, so fuel will ignite and maximum temperature rise will be noted. Okay, and then at the end release the pressure valve and take out the bomb. So at the end what will happen? See, when the process is over, you will open this lid of the calorimeter, you will take out the bomb, you will have to remove the oxygen first, and then you will have to open the bomb. Okay, so keep that thing in your mind. So now, sir, how it will measure the calorific value? Simple. See, heat given by the fuel is equivalent to what? Heat absorbed by the calorimeter and water. See, that will be the concept. Whatever amount of heat is liberated over here, from here, that will be absorbed by this water, right? So now, what amount of heat will be liberated? So mass of that fuel into its calorific value, because you know calorific value is what? Amount of heat released by burning a particular fuel, right? So that is equivalent to heat absorbed by the water as well as calorimeter. So heat absorbed by the calorimeter is known as MC delta T. MC is what? Mass of calorimeter. Cc is what? Specific heat of calorimeter. And delta T is what? Temperature rise in calorimeter. बराबर. Delta T is we have already noted down. Okay, MC and CC will be given by the manufacturer. MW and CW. See, mass of water will also be given by the manufacturer. Generally, according to your model of bomb calorimeter, you have to predefine. You will be having predefined level of water or mass of water that you have to take over here. For example, 2 liter or 3 liter. Okay, so mass of water will be known. Specific heat of the water, that is also known, and delta T you have noted down. So you have all these terms. You also have mass of fuel, that is sample mass. So now you can substitute the value over here and can find out the calorific value. Okay, in modern bomb calorimeter, 2 types of calorimeters are there. That is semi-automatic and automatic calorimeter, fully automatic. In semi-automatic calorimeter, these calculations are directly done in a unit, computerized unit. So you will have the final value of the calorific value. And in fully automatic calorimeters, also you will have the final value, and you will be able to visualize the graphs on the computer screen during the combustion of the fuel. Okay, so these are the arrangement right now in the bomb calorimeter. Okay, so these bomb calorimeter are generally used in research and development wing of many industries, wherein the amount of heat liberated by any fuel is very much important and crucial parameter. There the bomb calorimeter will be used. Okay students, so you can use liquid also and solid also in this kind of bomb calorimeter. Liquid means petrol, diesel, kerosene, etc., and solid means benzoic acid or coal, etc. Okay, so notations that are used, the meaning of the notations are written over here. Okay, so you can refer that. So we will keep up to this point. Thank you.